So welcome to the video. Today we're going to take a look at how to do a paired t-test on version 31 of SPSS. So we're going to use this test when we have a within participants or within subjects categorical variable comprised of two levels, and when we have a continuous dependent variable. So for this example, we are going to imagine that we have a new treatment for blood pressure, and we're going to measure blood pressure using millimeters of mercury. So that's what these numbers represent here. So these represent blood pressure scores before the treatment, and in this column on the right we have blood pressure scores after the treatment. So we're going to use the paired t-test to see, is there a significant difference in blood pressure between these two time points? So to start off with, let's go over to SPSS and we'll go down to variable view, and then we're going to put like before in this top cell in the name column. So that's before treatment. We can put treatment there as well. So we'll put an underscore and then treatment. And we have to use an underscore there because we can't use a space. So then let's put after underscore treatments. And then we're just going to use this measures column here to indicate that we have scale data, which is similar to continuous data. Then we'll go over to data view, and we can see that we have those two variable names at the top of these two columns. So we can just go to this Excel file and we'll select the top left piece of data. We'll go down to the bottom right piece of data and click that while holding shift. Then we'll go to Command or Control C to copy those data. We'll go to the top left cell in SPSS and we'll go to Command or Control V to paste those data in. If that doesn't work, which is sometimes the case for some reason, we can go up to Edit and then down to Paste to put those data in. So this test assumes that the differences between the time points are normally distributed. So to check this assumption, we actually have to create an additional variable within SPSS. And so to do this, we can go up to Transform and then down to Compute Variable, and then we can transfer before treatment over to here using this arrow. Then we can just click this minus button, and then we can transfer after treatment over here using the arrow as well. And then we can just give a name to this new variable that we're going to create. So let's call that difference, and then we'll go to OK. And we can see now that we have this column that has scores that represent the difference between these two columns. For example, 140 minus 123 is 17. So that's what we have all the way down. And now we can do a normality test to determine whether the values in this column are normally distributed. So to do this, we can go up to Analyze and then down to Descriptive Statistics, then across to Explore, and then we can transfer this difference variable to the dependent list, and we can go to Plots, and we can untick stem and leaf, we can tick histogram, and we can tick normality plots for tests. Then we can go to continue and then to OK. And then I'm going to look at this test of normality table, and we have two options here. So we have the Kolmogorov-Smirnov test and we have the Shapiro-Wilk test. And we typically use this test on the right when we have fewer than 50 participants or data points, and this test on the left when we have more than 50 participants or data points. And the DF column in this table actually tells us how many participants we have. So we have 30. So obviously that's less than 50. So we're going to focus on this Shapiro-Wilk side of the table. And what we want to see is that we have a value in the SIG column above 0.05, as that would suggest that the data are normally distributed. So here we can see we have a value of 0.871. Of course, this is bigger than 0.05. So this does suggest that the data are normally distributed. And if we scroll down slightly, we can find this histogram. And what you want to see with the histograms when you're checking normality, at least, is that you have something resembling a symmetrical bell in your graph. So this actually looks quite good. It's not perfect. We have like a bit more on the left than we do on the right, but this looks to be quite consistent with a normal distribution, which corresponds with this high value here. So it looks like the differences are normally distributed. If you find that they're not normally distributed, you might consider doing a Wilcoxon signed ranked test instead, which is the non-parametric equivalent of the paired t-test and doesn't assume that you have normally distributed data. So let's get on with running the test. So let's go up to Analyze and then down to Compare Means and Proportions. And then we're going to go to Paired Samples t-test, and then we just transfer both of these levels of the independent variable over to these slots here. So I've selected them both. Then I'll go to OK to run the test. So if we take a look at this paired sample statistics table, we can see that we have a mean value of about 132 before treatment and we have a mean value of about 114 after treatment. So we can see that blood pressure has decreased based on these two means, but we don't yet know whether that difference is significant. So to determine this, we need to look at this paired samples test table, and specifically we need to look at these p-values over here. So we actually have two options. We have a one-sided p-value and a two-sided p-value, and we would use this one-sided p-value if we had a one-sided or directional hypothesis. So in this case, that would be something like it was hypothesized that blood pressure would be significantly lower after treatment compared to before treatment, and we would use this two-sided p-value if we had a two-sided or non-directional hypothesis, which in this case would be something like it was hypothesized that there would be a significant difference between before treatment and after treatment with respect to blood pressure. So the one-sided hypothesis is more specific. So let's imagine that we had a one-sided hypothesis, and we can see here that we have this p-value of less than 0.001, and as this is less than 0.05, it indicates that there was a significant difference between before and after treatment with respect to blood pressure. So that's essentially how we interpret the results of the paired t-test, but let's now take a look at how we can report those results. So I have this example here, and I've said that a paired t-test was conducted to compare blood pressure before and after treatment, and then I've said that a Shapiro-Wilk test indicated that the differences between the time points were normally distributed, and then I've inserted these stats here. So let's take a look at where those stats come from. So we're looking at this test of normality table, and we can see that here we have a statistic. So this is the W statistic value of 0.982, which in the results we've just rounded to 2 decimal places. We have a degrees of freedom value of 30 and a p-value of 0.871. And there's the degrees of freedom value, and there's the p-value, otherwise known as a sig value. Next we get on to reporting the results of the t-test itself. So I've said that blood pressure was significantly higher before treatment compared to after, and then we've inserted some means and standard deviations for both of those time points. So we have a mean of 132.47 before treatment, and we're getting that from this table here, paired sample statistics, before treatment, mean 132.47 if we round this to 2 decimal places. We also have a standard deviation of 10.14 to 2 decimal places, and that's what we have here. And then we just have the means and standard deviations for after treatment, which we're getting from here and from here. Next we have the results of the t-test itself. So we've said that t equals 12.74, and we're getting that from this paired samples test table, where we have this t column and we have a value of 12.74. We have a degrees of freedom value of 29, that's what we have in brackets here, and we have a p-value of less than 0.001, and that's what we're getting from here. Finally, we have this sentence which says that the effect size was large, and we report a Cohen's d-value of 2.33. So that Cohen's d-value is an effect size statistic, and it's coming from this pair samples effect sizes table, and from this Cohen's d row and this point estimate column, where we have a value of 2.33 if we round this to 2 decimal places. And I've described this as a large effect size, and that's based on these criteria in this note here. So typically values between 0 and 0.2 represent very small effects, those between 0.2 and 0.5 represent small effects, those between 0.5 and 0.8 represent medium effects, and those above 0.8 represent large effects. And this also applies if we're looking at negative values as well. So here we have a positive value of 2.33, and as this is bigger than 0.8, I've described that as a large effect up here. So that's about it for the paired t-test on version 31 of SPSS. I hope that was helpful. If you have any questions, just let me know in the comments and I'll try to get back to you. Thank you very much for watching, and I'll see you next time.